7.2 is about solving exponential equations. So in the first section we talked about graphing them and looking at the domain and range. Now we're going to actually have to solve them and figure out how to figure out what the variable has to equal. And our strategy in 7.2 is fairly simple. What we want to do is get the bases to be the same on both sides of the equations. And then we're going to set the powers equal to each other and solve it that way. Okay. In everything in 7.2, you will be able to make the left-hand side base and the right-hand side base be the same. Sometimes you're going to have to change both bases. Sometimes you're only going to have to change one. When we get into 7.4, I'm going to show you how to solve exponential equations when you can't get the bases to be the same, because sometimes you can't. But for 7.2, we'll be able to get them all to be the same. So the key thing is, and this is just like when we were looking at division with exponents in chapter 6, we wanted to get everything to the smaller base. And in this case, what we want to do is see, is there a way to write 64 as 4 to some power?
Yeah.
What would it be?
Third power.
It's 4 to like 3.
4 to the third. So what we're going to do, the left-hand side stays the same.
I know how to do this.
The right-hand side changes to 4 to the third. Okay? And once the bases are the same, it's just a matter of setting the powers equal to each other. Okay? So in this case, I then can really stop thinking about the bases and just go 2n minus 1 equals 3. So go ahead and finish that one up. So when I finish solving this, what does n equal?
2.
2. Okay? So add 1 divided by 2. Now let's do a quick little check, make sure this works out okay. 2 times 2 is 4, minus 1 is 3. 4 to the third does equal 64. Okay? So that's all you got to do. Sometimes you're going to want to change both bases when you can't get it to be the same. You could have made this 2 to the second and then made this 2 to the sixth. It would still work out. I want to show you what happens when we have exponents on both sides. Okay? Let's look at the next example. So in this case, I have exponents on both sides and I have variables on both sides. The strategy is still the same. Try to make the bases the same. And in this case, 5 can't really be broken down, but can I write 125 as 5 to some power?
Yes. 5 to 3.
5 to the third. Okay, so this still stays 5 to the 5x. Now here's what I'm going to do. I'm going to write 5 to the third, and that is just going to be multiplied by that x plus 2. Okay. The reality is it's a power to a power. Okay, 5 to the third to the x plus 2. So when it's power to a power, what do you do with the powers? You multiply. So in reality, let me kind of move this a little bit. In reality, what we have here is 5 to the third, and then it's raised to another power. Power to a power. But when I set it up to solve, it's really, since it's power to a power I multiply, you're just solving this equation. Okay. So to your question before, Chris, if I had to switch the other one, you'd have to do some multiplying there. So go ahead and finish this one up. So let's check. So I get 5x equals 3x plus 6. So 2x equals 6. So x equals 3. Do a quick little check. That's 5 to the 15th. Okay, this is 125 to the 5th. So you might not know what 125 to the 5th is, and let alone 5 to the 15th. You could plug that in and check, but at the same time, if I plug it in here, this gives me 5, and 3 times 5 is still 5 to the 15th. Okay, so that's the first part of what you're going to do. Like I said, it is possible that you might need to change both of the bases to get them both to a smaller base, and you have some homework that is like that, so you have to watch out for that. Then we have a second part of this that we need to go over. So the next part of what we're going to be doing is word problems, okay? And this is in your book, or you can take a picture of this screen. It's up to you. Let me see if I can figure out what page it's on. So, page 1053. Alright, I gotta change off of that. Alright, so let's talk about what's going on here. And actually, this type of equation is really useful for a couple things. One, if you decide at some point soon that you want to start investing money in some type of account, this is how the money is calculated, how much money you'll have after a given period of time. And the sooner you guys can start investing money into an interest-bearing account, the more money you're going to have later. Your parents, hopefully, when you were really little, started a college savings account for you, and it uses these principles to calculate that money. Okay. The only difference is most of the time the interest rate changes throughout the course of the account, but this also works for not just investments. The same ideas work for car loans and home loans and things like that, so you can figure out how much money you'll end up spending in the long run. But long story short, let's talk about this particular problem, and we're just going to work through this. So this A is the amount of money that you have after a given period of time. Okay. Now, the time, T, is in years. So if your problem is not written in years, it gives you a certain amount of time that's not in years. You're going to have to convert it to years. And if you think back, I think it was chapter 2 test maybe, I gave you a problem where you had to plug everything in, and I gave it to you in months and you had to convert it to years. Make sure you do that. Principal is the initial amount that you invest, that you start with. So let's say you wanted to start with a $100 investment and hope for that money to build over time. That's the principal, the initial amount. The annual interest rate is R. Okay. And N is the number of compounding periods each year. Now here's what that means. Okay, so when we talk about compound interest, what we mean is that you take that initial amount, you multiply it and increase the amount, hopefully, and then when it gets compounded again, you take the new amount. Instead of always starting with the initial amount, you take the new amount and you increase it from there. So that's what compound interest means. Any of you guys who have a savings account use simple interest, okay? So it's just a one-time deal. It doesn't kind of keep building on itself. It just gets multiplied by the amount that's there instead of increasing every time, okay? So in order for us to do this, we have to understand the different types of compounding periods that you will face and know what they mean. So first of all, if something compounds annually, right? How many times a year do you think that would calculate? Once a year, okay? That's what annually means. Compounds annually means it will be done once a year. The other kind is compounds monthly. So what we have to do with this is always transfer it to how many times per year is this. So if it compounds monthly, how many times a year is that going to be? 12. So it means 12 times per year. Okay. There's going to be some problems that you're going to work on that will say that I didn't add to this. If you want to add to it, you can. If it compounds quarterly, every quarter is how often? 4 times a year. Okay, every 3 months, 4 times a year. So if you see quarterly, that's what that means. Another one will be weekly.
52.
Exactly. So that means it'll do 52 times a year. All right. Now the next two can be a little tricky because they sort of contradict each other, in my opinion. All right. So this one is bi-weekly. Is it 2 times per week, or is it every 2 weeks?
It's 2 times a
Every
week.
2 weeks. No, it's not.
So you go 1 week, then you don't 1 week, and then the next week you go.
Every
Per week.
every other week, which means 26 times a year. So, many jobs pay you bi-weekly. How many of you have a job? And you get paid every 2 weeks? Okay, that's bi-weekly. You get paid every 2 weeks. That's how we get paid here at school. We get paid bi-weekly, which is every 2 weeks. every other week. Okay.
I'm not telling
Now, the other one is bi-monthly. Here's where to me it seems confusing. Because if we use our idea for bi-weekly, bi-monthly should be every other month. But it's not. Bi-monthly means twice a month. So to me, this is where our English language we have some issues with
So it would be bi-weekly.
Evan,
No, bi-monthly means how many times a month?
Twice.
Twice a month. Which means, actually that's how we get paid. No, that's right. We get paid bi-weekly. Bi-monthly means twice a month. So a lot of times it's set up like this. You get paid on the 15th of the month and the 30th of the month.
Wouldn't
Regardless.
that be like count bi-weekly though, because it's still every other.
Well, let's talk about how many times a year is bi-monthly if it's 2 times a month.
6. Oh, 2 times a month?
Yep. 24. So right, it's very close, but it is different. And here's the thing.
That's
And here,
so stupid. I'm sorry.
Okay.
That's just-
okay, thanks for sharing your opinion. Now, here's the thing. When you get paid bi-weekly, if you establish a budget, like my home budget is based off of getting paid twice a month, which is true for 10 months out of the year. But 2 of those months every year, I get a third paycheck. Right? Because bi-monthly is twice a month, which is 24.
You get
But if
paid-
I get paid every other week, I'm actually getting paid 26 times a year, which means if I budget my money based off getting paid twice a month, I've created a situation where there's 2 months out of every year where I sort of get an extra paycheck, and that's how I come up with some of my savings. Okay? When you get there in your life, when that matters, and it's years from now for most of you, if you want help, feel free to email me. Alright, here's the type of problem we're going to look at. Here is the example. An investment account pays 4.2% annual interest compounded monthly. If $2,500 is invested in this account, what will the balance be after 15 years? This is a realistic type of problem. There are investments out there like this, where you can guarantee the interest rate, there's low volatility, meaning there's low risk of losing money. Okay, there are things called bonds, mutual funds, those types of accounts where you're going to make money. Bless you. Typically, when you're guaranteed to not lose money, the interest rates are going to be lower. But once you put it in the account, you just leave it there. This is why, for you guys, the sooner you can start investments, the better, because time is on your side. The longer it can sit in that account, the more money you will make. Think about our graphs that we looked at, right? And before we get into this actual problem, think about our graphs. Our graphs would look like this. They were climbing, 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 then all of a sudden they took off. This is how compound interest works. It might take 15 years to really start climbing. But once it starts climbing, it climbs really fast. So that's why, like I said, time is on your side. Me, not so much, because I don't have as many years ahead of me, hopefully, that you do. Which means the more time ahead of you have, the longer your investments can accrue. All right, anyway, let's get to the actual problem. Here's the way I like to set this up. First, I write the equation down. I write the formula down. Because I need to do it and practice it a bunch of times until I get good at it. And I got to remember what everything stands for. So the next thing that I do is make a little, I don't know, it's almost like a table of all the things that I need to know in order to use this formula. And I'm going to fill it all in based on the problem. And then once you do that, you plug it in and on your calculator and it spits the answer out. So P is the principal. My starting amount. What is my starting principal in this problem? $2,500. Okay? Time has to be in years, so how long is the investment going to sit? 15 years. It's going to sit for 15 years. Now the rate has to be converted into a decimal. So in this problem, the rate's 4.2%. What is that as a decimal?
0.042.
0.04. Okay. And then the number of compounding periods per year. So it's compounded what? Monthly, which means how many times a year? 12. Okay. So now once I have all this information, it's really just a matter of plugging it in, and I want you to plug it all into your calculator. Just be careful. Okay? Here's a couple things. Because when we plug it all in, this is what it looks like. On your calculator, the one place you want to be careful is right here. You probably want to put all of that, the interest rate divided by the time, in its own set of parentheses.
Wait, what is n equal 12?
Number of compounding periods. Okay? So, the rest of this you can put straight into your calculator. With your graphing calculators, when you hit that exponent button, so long as you're up in that superscript, you can just put 12 times 15. If you want to calculate it, that's fine. I do not recommend dividing this out. I recommend putting this all in the calculator as it is. Okay, so, looks like some of you got it already. Take another 30 seconds. Here we go. So, your answer should be $4,688.87. I want to think about this for a second, okay? This person who made this investment did nothing other than find that investment and put $2,500 in. And to you right now, probably $2,500 seems like a lot of money. Soon, it's not going to seem like a lot of money. But you could change that amount. Let's say you wanted to invest $100. That's what seems reasonable for you to do right now today. Okay, maybe it's $50, maybe it's $20, I don't know. Ultimately, this person, in 15 years, by doing nothing, made over $2,100. Okay? They found a low-risk investment, and they just let the money sit there. And if you can do that sooner rather than later, think about it. 15 years from now, you're still very young. Right? 30 to 32 years old. Very young.
Yeah, that's kind of old.
I understand that you think that's old. But go ahead and do this problem again and change the number to 30 instead of 15 years. So 30 years. So you'll be my age basically. Okay? 46, 47 years old.
21. 20.
Yes, I'm 20. Thank you. So just plug in 30 and let's see what you get. Again, just let it sit there.
Like AG notes.
$8,000.
So you went from making $2,100 to almost $8,800. So you went from making $2,100, to making $2,100 to making $5,300 by again doing nothing. Okay? If you wanted to play around with it and change the initial amount, you could do that. Look,